The standard model of cosmology is, by 2024 measurements, fractured at its quantitative core, not as philosophy, not as interpretation, as arithmetic. Two independent determinations of cosmic expansion now disagree at 5 sigma significance, same statistical threshold used to confirm Higgs boson. One value comes from oldest observable light, another comes from stellar explosions in relatively nearby universe. Each method is precise, each method is repeatable, yet both cannot describe one self-consistent cosmos under same physical framework. Central question is direct. How can one universe yield 2 incompatible expansion rates, and what missing physics sits inside that gap? Pause there. Hubble constant, H0, measures present-day expansion rate of universe. Unit, kilometers per second per megaparsec, can feel remote, so convert it to motion. 1 megaparsec is about 3.26 million light-years. For each megaparsec separating 2 galaxies, expansion adds recession speed. If H0 is 70, then pair of galaxies 1 megaparsec apart separates at 70 kilometers per second through expanding space. At 2 megaparsecs, speed doubles. From that single parameter, modern cosmology derives first-order structure, inferred age of universe, dark energy density, and large-scale geometry of space-time. Shift H0 by few percent, and downstream model parameters move with it. For decades, strategy was straightforward. Reduce uncertainty, improve instruments, converge on one value. Convergence never arrived. First route comes from Planck satellite, active 2009 through 2013. Planck mapped cosmic microwave background, relic radiation released about 380,000 years after Big Bang. Tiny temperature anisotropies in that field encode early universe composition and curvature. Fit those fluctuations within base LCDM model, and final full mission Planck result gives H0 equals 67.4 plus or minus 0.5 kilometers divided by S divided by MPC. Error bar there is exceptionally tight, below 1%. It is inference of high precision from universe in infancy. Second route avoids early universe fit and measures late universe directly. SH0ES collaboration, led by Nobel laureate Adam Rees, builds distance ladder in steps. First rung uses Cepheid variable stars, pulsating supergiants whose period luminosity relation reveals intrinsic brightness. Next rung calibrates type Ia supernova luminosities using Cepheid distances. Final rung extends to roughly 300 high redshift type Ia supernovae to recover expansion rate. Their 2022 result, H0 equals 73.04 plus or minus 1.04 kilometers divided by S divided by MPC. That value is also precise, also reproduced across analyses, and it sits 5.6 kilometers MPC above Planck prediction. Numerically, gap is about 9%. In daily life, 9% sounds small. In precision cosmology, with both pipelines claiming sub 2% control, it is severe. Tension now exceeds 5 sigma, corresponding to probability below 1 in 3.5 million. That mismatch is random fluctuation. For scale of confidence, comparison is exact and historical. CERN announced Higgs discovery in 2012 only after crossing same 5 sigma threshold, so this is not rounding noise. Not teams arguing over ambiguous plots. It is conflict between 2 of most accurate measurement programs ever built. One reading universe at 380,000 years, one reading it at roughly 13.8 billion years, returning values that cannot both be right under unchanged LCDM physics, and decade after decade, discrepancy persisted. Natural first hypothesis was systematic error. If one method was biased, sharper instruments should compress disagreement over time. Observed trend went opposite way. As calibrations improved, as datasets expanded, as analysis pipelines were stress tested, tension held near same separation. Local measurements repeatedly landed high. often in 70 to 76 kilometers MPC range, with mean near 73. Early universe inference from Planck remained near 67 to 68 under base model assumptions. Instead of collapsing toward midpoint, two bands stayed apart. Then James Webb Space Telescope entered test directly. Webb re-observed Cepheid hosts with finer infrared resolution and cross-checked Hubble Space Telescope photometry. Result did not rescue systematic crowding explanation. Webb confirmed Hubble-based ladder. In 2024 analyses, unrecognized Cepheid crowding was rejected at 8 sigma confidence. In largest Webb study to date, same supernova host galaxies yielded H0 equals 72.6 kilometers divided by S divided by MPC, nearly matching Hubble's 72.8 for those systems. Most intuitive escape route, local ladder must be instrument artifact, weakened further under independent telescope with different optics, detectors, and analysis constraints. Gap remained. Measured certainty is where story begins. Disciplined unease is where data leads, because if both pipelines are internally consistent, then inconsistency may sit deeper, not in detectors, but in model connecting early universe to late universe. What follows is that narrowing corridor, where each eliminated error source leaves less room for comfort and more room for new physics. The Hubble constant sits 9% higher than predicted. Before anyone rewrites cosmology, every instrument must be interrogated. Calibration drift in the distance ladder's geometric foundation, photometric crowding, background starlight bleeding into Cepheid measurements in dense galactic cores, dust reddening models that underestimate how much interstellar material dims a supernova's light, selection bias favoring intrinsically brighter Type Ia events, methallicity shifts across Cepheid populations that alter their period luminosity relation by fractions of a magnitude. Each failure mode is real. Each has been measured. Observational cosmology has spent decades isolating them, quantifying them, building statistical frameworks to absorb their effects. The SH0-ES collaboration, supernova H0 for the equation of state of dark energy, constructed its measurement to survive exactly this kind of scrutiny. Led by Nobel laureate Adam Rees at Johns Hopkins, the team built a 3-rung distance ladder. First rung, geometric parallax distances to nearby Cepheid variables. Second rung, those same Cepheids, calibrating the intrinsic brightness of Type Ia supernovae in their host galaxies. Third rung, roughly 300 high redshift Type Ia supernovae, now standardized candles whose recession velocities trace the expansion rate directly. The 2022 result, H0 equals 73.04 plus or minus 1.04 km divided by S divided by MPC. That uncertainty is narrow. It reflects years of refined photometry, deliberate host galaxy selection, statistical treatment designed to account for known systematics. The value it centers on sits 5.6 kilometers MPC above the early universe prediction, a gap exceeding 5 standard deviations. The audit continues, and for years, the most plausible explanation was also the most mundane: stellar crowding. Hubble Space Telescope observes Cepheid variables in the dense inner regions of distant galaxies. At Hubble's angular resolution, faint background stars blend into a Cepheid's point spread function. Unresolved light. The Cepheid appears brighter than it is. Brighter Cepheids imply shorter distances. Shorter distances mean faster inferred expansion. If crowding were systematically inflating Hubble's photometry, it could account for the entire discrepancy. This was not a fringe objection. It was the leading instrumental hypothesis. What followed was the test designed to resolve it. James Webb Space Telescope launched December 25, 2021. Reached operational orbit at the second Lagrange point 1 month later. Its 6.5 meter primary mirror collects over 6 times the light of Hubble's 2.4 meter aperture. More importantly, Webb observes primarily in infrared wavelengths. Where stellar crowding resolves more cleanly, dust extinction diminishes, and Cepheid period luminosity relations tighten. If Hubble's Cepheid photometry had been corrupted by crowding, Webb would see it. Sharper stellar profiles, cleaner fields, different distances. The SH0ES team obtained Webb observations of Cepheid variables across host galaxies already measured by Hubble. They correlated the new infrared photometry with Hubble's optical data, star by star, galaxy by galaxy, point by point. Webb did not correct Hubble, it confirmed it. Adam restated the result without qualification. We've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence. The weight of that statement does not rest on authority, it rests on what the data shows. The crowding hypothesis, unrecognized contamination of Cepheid photometry, was rejected at 8 sigma confidence in a 2024 paper published in the Astrophysical Journal Letters. 8 sigma. Particle physics declares a discovery at 5. The crowding explanation did not weaken under Webb's scrutiny. It was statistically excluded. The expansion rate itself held. In the largest Webb study to date, all galaxies observed by both telescopes, together with their supernovae, returned a Hubble constant of 72.6 kilometers s MPC. Hubble, measuring those same galaxies, had found 72.8 kilometers s MPC. 2 observatories, different mirror geometries, different detectors, different wavelength coverage, different calibration pipelines, different eras of software, a difference of 0.2 km s MPC between them, less than 1/3 of 1%. The instruments are not disagreeing with each other, they are disagreeing together with the early universe. This is the moment the Hubble tension stops being an observational puzzle and becomes a theoretical pressure point. Instrumental doubt has been compressed to near irrelevance. The discrepancy survives improved angular resolution, extended infrared coverage, independent reanalysis of the same stellar populations across 2 fundamentally different telescopes. What remains is not a question about photometry or calibration or crowding. It is a question about whether the model connecting the universe at 380,000 years old to the universe at 13.8 billion years old is complete. If the late universe measurements continue converging near 73 while the early universe inference holds at 67.4, the pressure shifts, not gradually, decisively, irreversibly. From the instruments to the cosmology, they were built to test. LCDM has survived more observational impacts than any cosmological framework ever built. It reproduces large-scale galaxy structure, hydrogen-helium ratios from first minutes, fine-grained CMB temperature structure, and late-time acceleration attributed to dark energy. Competing models have not matched that breadth with comparable precision. That strength is also pressure point. Planck did not read today's expansion rate straight from sky. It mapped CMB anisotropies at 1 part in 100,000, then fit 6 parameters inside LCDM. H0 equals 67.4 km divided by S divided by MPC emerges from that machinery. Not isolated thermometer reading, but downstream consequence of framework assumed complete. That distinction carries real weight. Ultra-effective relativistic species, pre-recombination dark energy behavior, or sound horizon physics, and fitted H0 moves with it. So 67.4 is conditional, exacting, powerful, model dependent. Relax, completeness, and prediction breathes. Local ladder works differently. Cepheid variables calibrate type Ia supernovae across roughly 300 hosts. Periods are timed, flux counted photon by photon, luminosities cross-anchored, redshifts measured from spectra. Chain leans on stellar astrophysics and geometry, not global closure condition. 2 pipelines now stand face to face. One infers expansion through theory, other measures expansion, then asks theory to account for it. They remain separated by about 9%. If both instruments and analyses are functioning correctly, mismatch stops being nuisance and becomes evidence. During last decade, theorists opened more than 12 modification classes to standard cosmology. None hardened into consensus. Barrier is structural. ЛCDM is tightly interlocked. Pull one parameter to relieve Hubble tension, and stress appears elsewhere in fit. A leading proposal introduces early dark energy, short episode of accelerated expansion before recombination, around 380,000 years after Big Bang. That episode would shrink sound horizon, the standard ruler encoded in CMB. Scale ruler down, and same sky can imply higher present-day H0, nudging Planck-derived values toward low 70s. But same ruler is imprinted again in baryon acoustic oscillations, fossil sound wave structure traced by galaxy surveys. Those surveys constrain pattern independently, so move that helps H0 often degrades consistency with large-scale structure. One door opens, another narrows. Second class modifies early relativistic energy density. Extra neutrino-like degrees of freedom, or other light particles beyond standard model, can speed early expansion and shift inferred H0 upward. Then independent walls close in. Big Bang nucleosynthesis limits allowed species through primordial element abundances, while CMB damping tail constrains free-streaming era physics from another angle. Space that looks open at first, pass compresses under joint data. Third root changes late time dynamics. Dark energy that evolves, rather than remaining strict cosmological constant. This remains hypothesis, explicitly, with no direct confirmation to date. Any visual showing alternate expansion tracks is artist's impression, not observational footage. Across these families, same pattern repeats. A model can ease one dataset and tighten knot in another. No proposal yet passes all major constraints simultaneously without fine-tuning, added freedom, or both. Historical trend is the sharpest signal. As precision improved, discrepancy did not wash out. It climbed roughly 3 sigma, then 4 sigma, then beyond 5 sigma. That trajectory runs against expectation for ordinary calibration error. Random noise diffuse. Hidden systematics, once isolated, usually collapse under cleaner data. This gap endured through that process. Cosmology, therefore, is not in freefall. It is in compression. Measurements are more stringent than ever, and one constraint now resists full accommodation inside baseline LCDM. Stress point is not observational culture. It is assumption model already contains every relevant component. A decisive discriminator still lies ahead, not another circular reanalysis, not marginal recalibration of same ladder. A mission designed from inception to force falsifiable split between residual systematics and genuinely new physics. That observatory is no longer conceptual. Hardware exists. Systems are tested. Fuel is loaded. Launch preparation is active. The date is no longer abstract. It is scheduled. September 2026 marks scheduled launch window for Nancy Grace Roman Space Telescope, observatory whose core science agenda was shaped, in part, by discrepancy traced here from first measurement to latest confirmation. By now, corridor has narrowed to hard edges. Planck inferred H0 equals 67.4, PM 0.5, k-meters divided by EP divided by MPC from infant universe, reading temperature ripples imprinted when cosmos was 380,000 years old. SH0ES measured H0 equals 73.04, PM 1.04, kilometer divided by S divided by MPC in mature universe, using roughly 300 high redshift type Ia supernovae tied to local distance ladder. Webb then checked local side with independent optics and returned 72.6 kilometers S MPC, while rejecting most plausible Cepheid crowding systematic at 8 sigma confidence. Each pass tightened error bars. None erased gap. Opening question can now be answered without soft language. How can one universe yield 2 expansion rates that differ at greater than 5 sigma significance? Because both rates are measured correctly and discrepancy is physical. Mismatch is about 9%. Under current statistics, this is not one more noisy fluctuation expected to vanish with time. 1 in 3.5 to million odds are no longer persuasive refuge. What fails is not telescope. What fails is completeness in bridge model between early universe inference and late universe observation. That distinction changes tone of field. Tension is no longer treated as smudge on one detector, one calibration chain, or one analysis pipeline. It now reads like structural crack. Two verified systems, built differently and cross-checked independently, return incompatible answers to same cosmological quantity. Silence follows that realization. Then design requirements. Roman's contribution is not simply sharper pictures. Its wide-field infrared instrument surveys field roughly 100 times larger than Webb's NIRCam, allowing uniform supernova catalogs at scale unavailable to previous missions. Instead of stitching together observations from different telescopes, epochs, and calibration cultures, Roman can assemble thousands of type year supernovae under one instrument framework, with one photometric system, across continuous redshift span from nearby universe into era when dark energy began to dominate expansion dynamics. That homogeneity matters more than spectacle. SH0ES achieved landmark result with about 300 high redshift supernovae gathered across multiple generations of observatories. Roman is built to collapse that heterogeneity into controlled dataset, where instrumental differences no longer masquerade as cosmology. At same time, Roman will run 2 additional expansion probes, weak gravitational lensing and baryon acoustic oscillations. These are geometric methods, not ladder methods. They do not depend on Cepheid calibrations. They do not inherit same potential systematics. If all 3 channels, supernova ladder, lensing, and bow, converge near 73 from single platform, argument for beyond lambda, CDM physics hardens dramatically. If Roman's larger, cleaner samples drift towards 67, 68 unresolved ladder, systematics recover, explanatory weight, and standard model regains footing. So logic is binary, even if consequences are not. Either new physics becomes difficult to avoid, or known physics survives by passing harder tests than any it has faced so far. The Hubble tension does not reveal failure of measurement culture. It reveals measurement succeeding to point that theory is forced to answer. For more than a decade, teams improved calibration expecting convergence. Gap widened. Independent facilities were brought in, expecting one value to absorb other. Both remained. In experimental science, that pattern, increasing precision paired with increasing disagreement, is not signature of routine noise. It is what appears when model reaches limit of what it can describe. LCDM remains extraordinarily successful. Its account of CMB anisotropy, large-scale structure, and primordial nucleosynthesis is still among the most precise achievements in physical science. Nothing in tension erases that record. What has changed is narrower and more serious. Confidence that the baseline 6-parameter form includes every ingredient relevant to expansion history. Somewhere between recombination and now, something may have acted on cosmic expansion in a way baseline LCDM does not encode. Early dark energy, evolving equation of state behavior, an additional relativistic component, or mechanism not yet formulated. Today's data cannot discriminate decisively among these options. Roman was engineered to make that discrimination unavoidable. In that sense, precision cosmology has not stalled at paradox. It has transitioned to program. A falsifiable prediction stands in daylight. A mission with launch window exists. A survey architecture is defined. A decision tree is already drawn. 2 errors were measured. 2 methods were verified. 2 answers persisted. Conflict does not imply flawed questions. It implies that the translation assumed a grammar incomplete. When Roman reports, that grammar will be tested.